Dear children, now let's discuss section 5.3.2. In this section, we learn how to differentiate implicit functions, the derivative of implicit functions, and also the derivative of inverse trigonometric functions. Though we have taken down the results in the previous lectures, here we'll try to prove the case for few of the inverse trigonometry functions and start doing the problems. First, let's define what we mean by an implicit function. Suppose y is a dependent variable. Y is the dependent variable that depends on the independent variable x. X, the independent variable, then if the relation between x and y, that is f of x comma y equal to 0, can be rearranged as y is equal to phi of x, then we say this case as explicit function. If such segregation is not possible, otherwise our f of x comma y equal to 0 is called an implicit function, where we cannot arrive at such a relation. In this section, we'll find the derivative of such functions, and we also discuss the derivative of inverse trigonometric function. Though we have taken down the results earlier, let's have a quick recollection about the results. That is f of x and the derivative of f of x in case of the inverse trigonometric function. So the derivative of sine inverse x is going to be 1 by root of 1 minus x squared. The derivative of cos inverse x is minus 1 by root of 1 minus x squared. The derivative of tan inverse x is going to be 1 by 1 plus x squared. The derivative of secant inverse of x is going to be 1 by mod x into root of x squared minus 1, and the derivative of cosecant inverse of x is minus 1 by mod x into root of x squared minus 1, and the derivative of cot inverse of x is minus 1 by 1 plus x squared. In this lecture, let's prove a particular formula, one formula. The rest are similar follows, which you can try independently. Now, in this lecture, let's prove the derivative of secant inverse x. So, our aim is to find d by dx of secant inverse of x. So, let's assume y is equal to secant inverse of x. So, this implies our y lies between, y belongs to the open interval 0 to pi minus singleton pi by 2. That is the domain of secant inverse, that is the range of secant inverse of x. Here we consider the open interval 0 to pi because at 0 and pi the function is not continuous, secant inverse x is not continuous. So we omit y equal to 0 and y equal to pi and consider the open interval 0 to pi minus singleton pi by 2. So this implies applying secant on both sides, we get secant y is equal to secant of secant inverse of x, that is equal to x. Now differentiate with respect to x. Differentiating with respect to x, applying the chain rule in the left hand side, differentiating, that is d by dx of secant y is equal to d by dx of x. So we get differentiating secant y, we get secant y into tan y into dy by dx, that is by chain rule, is equal to 1. So we have dy by dx is equal to 1 by secant y into tan y, where y belongs to the open interval 0 to pi minus singleton pi by 2. So we may have to consider the two cases. Case 1, to the left of pi by 2, that is in open interval 0 to pi by 2, in which case secant y is greater than 0. So dy by dx is equal to 1 by x into root of secant squared x minus secant squared y minus 1. That is equal to 1 by x into root of x squared minus 1. Now consider the second case, the interval pi by 2 to pi. The interval pi by 2 to pi, which lies in the second quadrant, secant y is less than 0. So, dy by dx is equal to minus 1 by x into root of x squared minus 1. So, combining both the results, we get dy by dx, that is y is secant inverse of x, d by dx of secant inverse of x is equal to 1 by mod x into root of x squared minus 1. In similar way, the other results could also be proved. Now in the next lecture, we'll discuss the problems from the exercise. Thank you.